Hello everyone, this is Neeti Jindal. Welcome to KC's 8th session, Hardware Support for AI. Before we start, I have few announcements to make. Please note that this session will be recorded. And we have 5 papers in this session, 3 journal track papers and 2 work in progress papers. So each journal track paper, here the author will present a live 10-minute talk, and this will be followed by a 5-minute Q&A. For work in progress papers, the authors, they'll give a 3-minute live talk, and this will be followed by a 2-minute Q&A. You can ask your questions either in the chat or you can just unmute yourself and ask your questions directly. I would highly encourage to please unmute yourself and ask your questions directly to the authors. Also, I would like to request all our authors to please adhere to the timings. One more thing, we have a poster session later today. So you can meet authors there and can have a detailed discussion about their work. So maybe we can start with our first paper. Our first speaker is Sosei Keda. He'll be talking about hardware-friendly delayed feedback reservoir for multivariate time series classification. Sosei Keda, he received his BE degree from Faculty of Engineering, Kyoto University, Japan. He is working towards his master's degree at the Graduate School of Informatics, Kyoto University, Japan. Sosei, over to you. You may share your screen and begin.
Thank you for the introduction. Well, try it displayed properly.
Yeah, we can see your screen.
Yeah. Well, hello, my name is Sosei Keda. Thank you for this opportunity to talk to you today. The title of my presentation is Hardware-Friendly Multivariate Time Series Classification. In this presentation, I propose a computationally efficient reservoir computing method for multivariate time series classification. Here is the outline of this presentation. First, I will explain the concept of reservoir computing. Second, I will explain a key concept in this study, reservoir representation, and briefly review existing reservoir representations. Third, I will propose dot product-based reservoir representation. Then I will present an evaluation of the effectiveness of the proposed method. Finally, I will conclude the presentation. Reservoir computing is attracting attention as a machine learning technique for edge computing. There are 3 layers. First, the input layer converts the input signal into format suitable for entering the reservoir, and the weight is fixed. Second, the reservoir transforms the signal into a high-dimensional nonlinear vector. We refer to this vector as a reservoir state and to its components as features. The weight of the reservoir is also fixed. Finally, the output layer performs pattern recognition using a simple learning algorithm, and the weight is determined through training. The DFO is a realization of reservoir computing in which the reservoir consists of only one nonlinear element and a delayed feedback loop. Compared with other reservoir computing schemes, DFO is easier to implement as hardware because of its simple structure. The greatest obstacle in applying reservoir computing to real-world time series classification tasks is the transformation of features obtained via the reservoir. In general, the number of features obtained by the reservoir varies with the length of the input data series, thereby preventing the structure of the output layer from being fixed. Therefore, it is necessary to convert these features to reservoir representation. The fundamental requirements of reservoir representation are as follows. First, its size should be constant and independent of the time series. Second, it should retain information in a high-dimensional space. And finally, it should be easy to calculate. I will review the existing reservoir representations. First, last reservoir state after all the input series were entered was used as a reservoir representation. The number of dimensions available with this representation is nx and relatively small, so the prediction of reservoirs using the reservoir representation is less accurate than that using existing neural network-based classifiers, particularly for multivariate time series classification tasks. Second, in the DRS, the reservoir state at each sample time is used as a reservoir representation. As the DRS is available for every sample time, the outputs are calculated using the output layer. The mode of the T inferred labels is used as the output inference label. The DRS is often used for time series classification using DFO. This method also yields less accurate results, especially for multivariate time series classification tasks. Third, in the MRS, Tmax, which is the maximum series length of all possible inputs, is applied to all other inputs to equalize the features length. The greatest drawback of this representation is the difficulty in determining the necessary and sufficient Tmax value in advance. Setting Tmax to be too large would increase hardware resources. Fourth, in the OMS, linear regression is first used to predict the input that is one time ahead of the reservoir state. It shows better classification accuracy than LRS and MRS. However, OMS involves the computation of a high-dimensional inverse matrix, which increases the circuit size when implemented in hardware. Finally, in the RMS, linear regression is first performed to predict the reservoir state one time ahead. The number of features is larger than the OMS. As a result, the RMS exhibits even higher accuracy than the OMS, as the cost of calculating the inversion of an even higher dimensional matrix than the OMS, which leads to a larger circuit size. Here, we propose DPRR, which is a novel reservoir representation based on the dot product across reservoir states of different times. To eliminate the loss of features while retaining the information concerning time variation, we utilize the time evolution of the features with samples of shifted time. By shifting the dot product one time step and considering all node combinations, we can obtain the square of NX features, which are independent of the time series length while retaining the information of the temporal evolution. In addition, we added the reservoir state itself as a feature. DPRR is expected to be implemented more efficiently than OMS or RMS because it can be calculated by using only matrix multiplications. We will evaluate the proposed DPRR. Comparisons are made through both software and FPGA implementations, the former to evaluate classification performance, and the latter to evaluate hardware resource usage. For the FPGA implementation, we used Xilinx BTC-HLS as a high-level synthesis tool and Zinc 7000 as a target FPGA board. The numbers are represented in IEEE 754 floating point format, and the data paths were not pipelined. First, the effect of reservoir representation was studied. Here, MRS UPAT and MRX PAT are the maximal reservoir states with zero filling for the input and reservoir states respectively. The upper table lists the classification accuracy for each representation. Here, the number of the nodes of the reservoir is 36. LRS and DRS were less accurate than the other representations. Although the proposed DPRR is computationally efficient, it achieved equivalent or higher accuracy compared to OMS and RMS. Then the lower table presents logic synthesis results of OMS and DPRR. Clearly, DPRR is more computationally efficient than OMS. When NX equals 50, the number of flip-flops in DPRR is reduced to about a quarter of those in OMS, and the number of lookup tables is about 1/5. Next, we compare the proposed DFR with DPRR to those of the DFR using DRS and other machine learning methods. This figure compares the accuracy for 12 multivariate time series classification tasks versus the number of block ramps required for the FPGA implementation. The average rank is defined as the arithmetic mean of the rank numbers being the most accurate method at first. The smaller the numbers on both the horizontal and vertical axes indicated improved results. Yes, thank you. Methods based on DFR require much smaller memory footprint than most machine learning methods. This figure compares the accuracy versus the power delay. The smaller the numbers on both the horizontal and vertical axis indicate improved results. The proposed method, DFR-DBRR, operates with a power delay product that is 3 orders of magnitude smaller than that of FCN, but achieves nearly the same accuracy as FCN. In this presentation, I propose the computationally efficient resolver representation, namely DPRR, based on the dot product between features in the reservoir of shifted time. Then the DFR using DPRR was evaluated on 12 different multivariate time series classification tasks. The proposed method outperformed conventional machine learning methods in terms of power delay product and memory usage, being orders of magnitude smaller. Thank you very much, that's all.
Thank you very much. It was a very interesting talk. Let's move to questions. Anyone from audience or anything physically from Shanghai? You can type in your question in the chat or you can ask it directly. I think everyone is saving for the poster session. I have a quick question from my side. So do you want to talk about the area overhead of implementing this algorithm?
Sorry, I can't hear.
I'm just asking about the area overhead of implementing this.
What? Sorry.
No. My question is regarding the area overhead of implementing this, right?
Area,
right. So you are talking about the dot product, right? All the computation that you are doing to get your data. Did you try to get the area overhead as well?
sorry. I didn't know. Area, what?
So you are basically doing this computation, right? You talk about the memory uses that I understand from the FPGA part of it. But what about the computation overhead?
So,
okay.
Well, the number of the gate is not increased.
Okay.
Well, as to the number of the gate?
Correct. So I'm saying when you are doing all this computation, you are computing the dot product over there to identify, right? So how is it impacting in terms of area compared to the other machine learning algorithms? This seems to be much simpler, right? You are improving the accuracy, but then you would have saved on the area as well, right?
So, compared to FCN, the proposed method, the number of gate of the proposed method is much smaller than FCN.
I see. Okay. Thank you so much. If we do not have any other questions, maybe we can move to the next paper. Our next speaker is Shangyu Wu. He'll be talking about bits ensemble towards lightweight, robust deep ensemble by bit sharing. Shangyu Wu, he is a third-year PhD student at City University of Hong Kong. He is supervised by Professor Ju Jason Chen. His research interests include embedded system with machine learning and database with machine learning. Shangyu, over to you.
Hello. Hello, can you hear me?
Yeah, we can hear you.
Oh, thanks. Thanks for the introduction. Hello, everyone. This is Shangyu from City University of Hong Kong. And this work is done in collaboration with McGill University, City University of Hong Kong, Xiamen University, and the National Taiwan University. And the title of my presentation is Bits Ensemble Towards Lightweight, Robust, Deep Ensemble by bit sharing. Okay. Here is the background of this work. Sorry. The deployment of deep neural network models have been ubiquitous in our societies. But however, the single deterministic neural networks is always overconfident and on its prediction results, and is vulnerable under the data shift. Deep ensemble is a simple but effective way to improve the calibration of prediction results and the model robustness of to the data shift. So the reason behind it could be understood from this cartoon in the middle. Different members in an ensemble tends to identify different local optimal. Thus, an aggregation of them could achieve a better diversity. Also, each of them still makes mistakes. The prediction results could be improved by voting. However, the ensemble size increases linearly with the number of members, but the performance of ensemble models increases slower after a certain number of members. So this causes huge transmission and storage overhead when deploying the ensemble on the edge device. So the motivation of this work is to find a method that could reduce the size of deep ensemble, which is well adopted method for the improving of robustness and the safety of AI method. Okay, so first we test a simple idea of bit sharing. We let the members shares the quantization bits, and it works well. But the challenge is we need a parallel algorithm to train, and a differentiable algorithm to automatically determine the bit sharing. So in this paper, we asked this question first. If we quantize an ensemble, can we size? We first developed one-dimensional bit sharing scheme to test if this idea works. And as shown in the algorithm one, here basically sorts the quantization bits by its value and clusters the closed bits. And the clustering sensitivity is determined by a threshold called delta. And as shown in the experiments result on the right, the sharing bits with bit level greater than certain value will not introduce a loss of performance. And smartly searching for the hyperparameter data while saving more space without degradation of the performance. However, the one-dimensional bit sharing scheme cannot be executed efficiently for high-dimensional weights. And the cost for searching data is also quite high. So the solution is to turn algorithm 1 here to a parallel and differentiable bit sharing scheme. And here we present our framework. Our framework of bit sharing includes 3 major steps: class string bits and founding representation bits, and assigning the representation bits. All could be executed in a parallel and differentiable manner. We present the overview of our bit sharing methodology. In the middle figure, it shows the full precision ensemble, and different rows in different colors shows different members within an ensemble, and different columns in different transparency shows different quantization bits level. And the right-hand side shows the bit sharing quantization steps. The bit sharing is executed in 3 major steps. First, to cluster the quantization bits. Then we calculate the representation bits. And finally, we assign the representation bits to the members within the cluster. Equal B of the sets from different members are represented by the same bits. And on the left side, this figure shows the regular quantization bit quantization applied to the ensemble. Applying the regular quantization to the ensemble will ignore the numerical correlation of quantization bits. Therefore, it uses more quantization bits than our method. So the significant feature of our method is that these 3 steps are executed in differentiable and parallel manner. And here I will show a concrete example of our algorithm, our framework. So this example shows how to parallelizable and differentiable bit sharing scheme works. First, in the left up corner, the input is a weight matrix who have 3 members and 2 dimensions. We first sorted the matrix along the parameter dimension and record the original index with the matrix I, and the difference of nearby parameters are calculated and stored in the data matrix. And then we compare this matrix with the threshold to determine the representation bits. And a series of differentiable and scalable operations are executed for assigning the representation bits into the clustered members. It's worth noting that the hardest part is to turn the one-hot encoding to parallel and differentiable operation. So we design a novel method based on the RBF. You can refer to our paper. Back to the original location by the recorded index. And the significance of this algorithm is first, the process is required to execute only once for a quantization bit level. And as the whole process are differentiable, the threshold data could also be learned from the data without searching. And we also designed the matrix decomposition method to fully utilize the bit sharing and the encoding decoding scheme for the real implementation of bit saving. As for the implementation, we design a unified matrix decomposition for the convolutional layers and the dense layers to further reduce the model size and fully utilize our bit sharing scheme. We decompose the V matrix to two components, U and V. And each component has a dimension corresponding to the ensemble member. So therefore, our bit sharing scheme could be fully utilized to saving quantization bits of U and V. And the implementation of our idea of bit ensemble is based on the group convolution and normalization. So for the second, for the real deployment of our quantization scheme, we also design an encoding scheme for mapping the quantized shared weights to a dense sequence of the bits. And we will also design a decoding scheme to map them back. And as shown in the picture on the left, the dense bits sequence includes the meta bits and the pattern bits and the parameter bits. And then by properly design and implementation, the overhead introduced by the meta bits and pattern bits could be very small. So finally, we do some experiments to show the effectiveness of our method. So the experiment shows that our method achieves 22 times of model size reduction and with the better performance. And the training time is only increased by 36%. And in the experiments, we compare our method with the state-of-art Bayesian bit quantization and a quantized batch ensemble method. And the results show that our method maintains the highest accuracy and obtains the smallest model size with only 36% increase of the training time. And the performance on neural network calibration shows that the bit ensemble is well calibrated, and the expected negative correlation shows that also we let different members share the quantization bits. So diversity is not affected. And we also design a use case that the server encode the ensemble to a sequence of codes and then transmits them to an real edge device. As the edge device then can decode can recover the ensemble from the codes. So in the bottom left figure, we can observe that on a real edge device, the decoding process could be done in a few seconds. And with an efficient encoding and decoding scheme, our method achieves about 22 times storage space reduction compared with the regular quantization method. And future work, we will explore the possibility of bit sharing scheme under large-scale language model or fishing transformer models. Okay, that's all my presentation. Is there any questions?
Thank you so much. It was a very interesting talk. Do we have questions?
I have a question. Have you ever considered the activation quantization? Oh, thanks for your question. Yeah, so activation quantization is also a promising direction for the quantization work. So we will consider the quantization of activation in the future. Okay, thank you. Thanks.
Okay, we have time for one more quick question. Anything physically from Shanghai or from online? Well, I have a quick question. I just missed the part on the evaluation. So all the numbers that you have presented, are these the simulated, is it some simulation environment or you have done it on an actual system?
Can you repeat your questions?
I'm just asking all the experiments, right? Here, the accuracy numbers you are presenting. Are these the simulation numbers or these are from a device, the actual implementation?
Yeah. Do you mean we achieve similar accuracy? Yeah. So the focus of our the ensemble is to reduce the model size while maintaining the comparable accuracy, and we don't expect to improve the accuracy.
Okay. Okay.
Thanks.
Thank you so much. So we can move to our next presentation. Our next speaker is Soumik Sinha. He'll be talking about exploring bit slicing architectures for enabling FHE-assisted machine learning. Soumik is a PhD candidate at Indian Institute of Technology, Kharagpur, India, where he is working on the design and implementation of secure machine learning accelerators. His research interests broadly lie at the confluence of system security and AI. Soumik has prior research experience in the data mining domain. He also has a brief stint at Qualcomm. Soumik, over to you.
Hi, thank you for your kind introduction. I'm Soumik Sinha, a PhD student at IIT Kharagpur, and I'm going to present our paper on exploring bit slicing architectures for enabling FHA-assisted machine learning. This is a joint work with my collaborators at IIT Kharagpur, NTU Singapore, NIU Abu Dhabi, DTU Delhi, India, and University of Nebraska at Omaha. So the broad objective of this work is to design accelerators for secure machine learning workloads. And to motivate a context a little, when machine learning workloads run in the public cloud, they are often vulnerable to adversarial attacks or microarchitecture attacks, which can result to data leakage or even data manipulation. As a result, the classifiers can misbehave, and this could result in catastrophic loss to customers, mostly in business critical use cases like healthcare, finance, etc. So naturally, the plausible solution is encrypted analytics, where all the data will be encrypted in the cloud, and then all computations will be performed on encrypted data sets. And homomorphic encryption is a pioneering tool which helps us achieve this encrypted analytics, which offers two primitive operations, homomorphic addition and homomorphic multiplication. So in this setting, we have two parties, the client and the cloud server. The client first homomorphically encrypts the data, sends it to the cloud. Cloud performs all the analytical computations on the encrypted data and sends back the encrypted output back to the server for further decryption. Now, homomorphic encryption schemes can be broadly classified into three classes. The partial homomorphic scheme supports only either one of the homomorphic addition or multiplication operations. And somewhat homomorphic scheme supports both the operations, but a limited number of times. So here in homomorphic encryption, at each level of encryption, a ciphertext noise fits into the ciphertext, and as a result, this noise explodes goes up to a level where it cannot be successfully decryptable. That's why the somewhat homomorphic schemes suffer from a limited multiplicative depth issue. But fully homomorphic schemes actually solves this technique, and it's the most powerful and latest scheme, which uses bootstrapping to refresh the ciphertext at each iteration, and thus it allows arbitrary number of or arbitrary depth of addition or multiplication operations. So since our focus is on building encrypted ML approaches, we look forward to the state-of-the-art approaches like CryptoNets or Lola CryptoNets, both of which are built on top of Microsoft Seal encryption library. Now, they have huge memory bandwidth, and another pressing limitation of the existing literature is that since most of the existing schemes are built on top of leveled or somewhat homomorphic schemes, they can only implement approximated activation functions because higher degree polynomials are not supported due to the multiplicative depth issue of these encryption schemes. And even the most pressing challenge of the existing fully homomorphic encryption schemes is which roots from some of the most latest frameworks like Concrete ML, which is built by the Zama researchers. And they execute some floating point approximation tensors, which leads to huge accuracy drop for deeper neural nets. So to understand the performance challenges, we first take a quick look on how FHE or fully homomorphic encryption computations work. They always operate, the FHE operations are performed on bit level using homomorphic operations like multiplication and addition, and all these operations are reduced to bitwise Boolean gates like XOR, AND, or etc. So if all FHE operations are performed in bitwise manner, and FHE also implements bootstrapping for reducing the ciphertext noise, which also involves huge number of bit level operations. So to sum up the performance bottlenecks, this slide mostly sums up what major challenges which lie ahead. One is the ciphertext blow-up problem, where each plaintext bit in FHE or when they are fully homomorphically encrypted, they result to huge bits of ciphertext. And since in FHE domain all operations are done on bitwise manner, and the bootstrapping is also done individually on all the bits, this adds to the performance complexity manifold. And parallelly, there is another pressing problem due to this concrete like libraries which allows floating point approximation tensors, which results in decryption errors. Now, at one level of decryption, this might not be serious, but when these errors amplify with the deeper, as we go deeper nets, like the epsilon square, epsilon cube, they could be catastrophic. They could lead to accuracy losses, and results have also pointed out that. So we try to contribute mostly in these two cases. First, we try to propose a mathematically exact ML inference framework without excusing any sort of approximation as in the case of concrete. And then we also propose optimization techniques. Now we propose a perspective of optimization for the building blocks of any deep neural net or convolution neural nets in general. And we then design memory efficient accelerators, which actually employ some bit slicing based data packing wrappers to accelerate the computation of these building blocks, which are omnipresent in all deep neural nets or convolution neural nets. So this is the broad design stack of our framework, where we first start with a deep learning model. We first perform an int-age quantization. So this quantization is done deliberately to get rid of the floating point tensors, because floating point tensors lead to approximation errors as in the case of concrete. So first we quantize the tensors and get int-age tensors. Then you have a public implementation. So like Microsoft Seal library, NUFHE is a classic library which implements FHE based operations and offers an application suite for bit level FHE operations using those homomorphic gates. So these NUFHE operations are applied on top of the int-age quantized tensors. And on top of that application stack, we apply our bit slice based data packing techniques, which are just software architecture wrappers, which are implemented like bit slice register, but in the software stack. So first we take a look on the quantization experiments. So first we quantize or encrypted means all the data and all the ciphertext tensors. First we quantize them, and it has been experimentally proven that this leads to at most 2% accuracy loss. And our target use cases are most of the MNIST dataset and another mainly cracked building dataset, which is a classification task of classifying cracked images of cracked buildings. Both of them have around 56 to 60,000 data points, and we have also noted that it results in minimal accuracy loss. And this step is important because when we are doing the quantization, we need to ensure that there is no significant accuracy loss in the process. So then we look at a classic template of a convolution neural net to figure out and propose our optimization perspective that in any neural net, convolution blocks and the dense blocks are the most time consuming, or they eat up the bulk of the computation time. So this is our perspective that can we boost the performance of these two blocks and then accelerate the entire inference timeline to that. So for that, the most fundamental computation template for doing this speed up is the dot product, because dot products are the main workhorse for any convolution 2D blocks or the dense blocks which eat up the entire computation time, and that is a summation wi xi. So this is where we bring in our this slicing based data packing wrapper. So instead of doing a multiplication of or a dot product, we implement it as a repeated addition where we add xi wi number of times. Okay, and now instead of adding a single xi, we pack multiple xis, which in our case might be the data, means the image pixels, into a register, which is again implemented in software stack. So if we use n-bit registers, n ciphertext, individual bit positions of n ciphertexts are packed together in a register, and then they're added with each other. So this is a packed addition. And so there, if we see in this figure, on the left, there is a box which shows the bit slice representation. We have n bit registers. Each bit is responsible for adding the individual bit positions of the n ciphertext operands. And there are k pair of registers, like from reg 0 to reg k minus 1. This is for the individual bit position. Here we assume that we have k bit numbers. So from LSB, we have say MSB, where MSB equals to k. So there are k pairs of registers, and they are adding individual bit positions of n operands. And further, we extend it during the convolution block. This gives us a dramatic speed up, where if you note in the big box on the top left, there are three colored horizontal rectangles: the blue rectangle, green rectangle, and the orange rectangle. This blue rectangle signifies the computation template of the first convolution block. Again, the green rectangle signifies it shows the computation template for the second conv2D block, if we look carefully. And the final one is the n minus k plus 1th convolution block, typically in a n cross n, considering a setting where we have n cross n images and k cross k convolutions. Now if we take a look at there are 6 vertical dotted rectangles which are actually used for doing the bit sliced packing. So in the leftmost vertical dotted rectangle, all are actually convoluted with W11. It's a single weight. And there are P11, P12, all these pixels which are convoluted over the course of all these n minus k plus 1 convolutions. So we pack them in this register and thus get the acceleration. Now it should be noted here that the weights in this kind of models are usually taken as public. That's why the weight will be used as the iterator for doing the self addition, and these pixels will be self added. And then you finally unpack the numbers, get the result to get the acceleration speed up. Now finally, we have to also design the circuits for, since in FHE everything is done in bitwise Boolean circuits. First, we see how to implement average pool. For doing average pool, it is just division by 4. In encrypted domain, doing straightforward division is not possible because we don't know the loop termination criteria for doing repeated subtractions. So we do it by providing bit shifts to the right. And for doing max pool, today it is just selecting a maximum of a group of numbers. So for that, we first subtract two numbers in the FHE space, take the MSB and use it as a selector of a mux to select the maximum, and then it's just a cascade of mux which gives us a max pool to the circuit. Now we finally come to the result. So now we have actually showed that all the building blocks, how we have designed the circuits and providing the accelerations. Now if I'll finally come back to the results. So we try our implementation without bit slicing and with bit slicing significantly, and we do it on top of this NeFHE based FHE bitwise FHE implementation library. Without bit slicing, it takes 80 hours, while with bit slicing, a neural net evaluation which has around 50 neurons in 2 layers and a final layer of 10 neurons, which is an NNIST classification task. This takes 2.15 hours, which is a 37x speed up. Consequently, we also evaluate our performance of this bit sliced framework on a conv2D based architecture. And there the conv2D block takes 2.32 hours, while the total inference time, the single inference time, takes around 4.5 hours, again on the NNIST data set. Now all these architecture templates have been previously checked that whether their accuracy is correct or not. Now, but notably, although our approach is not pretty fast, but we'd like to note here that compared to some classic approaches like CryptoNets or Lola, they are very much memory intensive, whereas for some convolutions only it spans multiple GBs. Our entire inference has been computed within a peak memory usage of 700 MB. So that kind of sums up our framework. And in further more we try to we will try to evaluate with tougher, with bigger benchmarks like CIFAR 10 and provide some compiler level optimizations or different performance benchmarking schemes with various platforms. That brings to the end of this talk. Ask questions. Thank you.
Thank you so much. It was a wonderful presentation. We have time for just one quick question. Anyone from audience?
Hi, I'm just wondering if you're planning to open source this code.
Yeah, we are planning to do it. And since we have not done any evaluation on embedded platform, so everything has been done in the cloud. So we are planning to open source it very soon.
And then what types of speed up do you use for the evaluation? Is this CPU, multi-core evaluation, or using GPU acceleration?
No, it uses GPUs. So we are doing it with NUFHE libraries, and it has some inherent parallelizable gate constructs because everything is done in Boolean gates in FHE domain. So it uses interim GPUs to do those entity calculations. Yeah, there is a GPU-based speed up also.
All right, thank you.
Thanks a lot, Shamik. If we have more questions, maybe we can take it on the poster. We can move to our next presentation. Now we have 2 work in progress papers. The format is 3-minute live talk by the author and then 2 minutes of Q&A. Our first work in progress paper is by Yoshikazu Watanabe. The title of the paper is Object Detection, Acceleration Method by Improving Execution Efficiency of AI Device. Yoshikazu Watanabe is a researcher of Digital Technology Development Laboratories, NEC Corporation. He is in charge of research and development on AI acceleration, especially for edge environments. After he joined to NEC Corporation, he worked on internet technologies such as mobile IP, IPv6, OpenFlow, and acceleration of networking software and AI using FPGA. He is now investigating technologies for efficient AI execution with various devices, including CPU, GPU, FPGA, and disk. Over to you.
Thank you for the introduction. I'm Yoshikazu Watanabe from NEC Corporation. I present object detection acceleration method by improving execution efficiency of AI device. AI devices are now available, such as Intel's ASIC Myriad X and NVIDIA's Jetson. And the issues for motivation are that higher throughput object detection is always desirable and welcomed. And we consider there are 2 types of inefficiency in the current object detection with the AI devices. The first one, issue A, is that the computing resources are wasted due to the processing of background region. And second one, issue B, is that even when focusing on foreground region or region of interest with small input size, inference by AI devices typically suffers low device utilization. Then we propose object detection acceleration method by improving the execution efficiency of AI device. For the first issue, issue A, the method uses 2 types of one-stage detectors in combination. The first one, lightweight high-speed detector detects foreground candidate and remove background efficiently. After that, the second accurate detector refines the detection result. For issue B, instead of inferencing on each small candidate images, the method generates aggregated image by combining candidates to improve the device utilization. Thus, our method enables taking advantage of the processing capability of AI devices. With license plate detection example, I show the processing flow. Assuming multiple images from multiple cameras, after primary inference on n input images by a lightweight detector, the method combines the detection result and generates an aggregated image by placing the candidate images. Then it executes secondary inference on the aggregated image by an accurate detector to generate final accurate detection result. We evaluated the method with license plate detection task. Accuracy and throughput were compared with M2DET and YOLO-V5S baselines on 2 AI devices, and with almost no accuracy degradation, our method achieved roughly 8 times speed up on each device. We also made an evaluation with care detection test and pose estimation test, including PT and MS COCO dataset, and we confirmed that speed up ranging from 1.6 times to 5.9 times. And this slide concludes my presentation. Thank you for your attention.
Thank you so much. Any questions from the audience? Anything physically from Shanghai? Okay, I have a quick question. So have you observed anything sensitive that you have lost when you were doing this background removal, like some of the important information, any particular scenario that have come across?
Sorry, could you please repeat your question? Sorry.
I'm just asking, right, because you are working on the object detection and this is more related to the real life scenarios, right? Anything where you have lost the sensitive information while removing the background?
Basically, we are going to try find all possible candidates on the first phase. So basically, yeah, we are going to remove the background, but I use very low confidence threshold to catch all things in the first phase. After that, we refine the result to remove garbage. So we use all information from the input.
Okay, yeah, that's a very interesting work. Thank you so much.
Thank you.
We can move to our last work in progress paper. Our next speaker is Yiming Li. He'll be talking about his work, Cooperative MLP Mixer Networks, Inference on Heterogeneous Edge Devices through Partition and Fuse. Yiming Li, he received the BS degree from the School of Software Engineering, East China Normal University, Shanghai, in 2020. He is currently pursuing the MS degree with the School of Software Engineering, East China Normal University. His research field mainly includes software hardware co-design and DNN model inference at edge. Yiming, over to you.
Thanks for the introduction. Hello everyone, my name is Yiming Li from East China Normal University. Today I would like to give a presentation on our work in progress paper, Cooperative MLP Mixer Networks Inference on Heterogeneous Edge Devices through Partition and Fusion. This presentation consists of 5 parts. Firstly, I will introduce the background, motivation, and the problem formulation. Then I will introduce our partition and fusion model or fusion method. Finally, I will introduce a real-world case study and give the experimental result and conclusion. Deep neural network has been applied in many real-time scenarios, such as healthcare, autonomous driving, and intelligence transportation. In this paper, we study a DNN application scenario as shown in the figure. DNN module is first trained on cloud server, and then be deployed on each device for real-time inference. There are 2 issues in this scenario. Firstly, the development of DNN architecture makes DNN hard to parallel and need more computation resource. The other issue is, although each environment has stable network condition, it still suffers from high communication costs and a constrained resource. We study a newly proposed DNN architecture called MLP Mixer and propose a novel partition and a fusion method to deploy it on each devices. Here is the problem formulation. For a DNN inference scenario with K devices and with network bandwidth B, our goal is to find a method pi to minimize the total runtime We denote layer as a tuple, which consists of communication, memory, layer size, and computation. We propose 3 partition methods for MLP layers in MLP Mixer, which are data partition, model partition, and data model partition. We also propose fusion method to further reduce communication cost. If we use 2 dense layers, we can use data partition and data partition. We can also use model partition and data model partition to fuse 2 dense layers. In MLP Mixer model, we use FC, GLU in MLP. We use layer normalization, MLP, and add in channel mixing. We use transpose, MLP, and add in token mixing. We conduct a case study on the real-world setting. We deploy MLP Mixer B16 with 300 Mbps network bandwidth on the heterogeneous and the homogeneous scenarios. Here are the experimental results. When the number of devices increase from 2 to 6, our partition and fusion method can achieve 1.01 to 1.27 speed up and 1.54 to 3.12 speed up with heterogeneous and homogeneous devices, respectively. In this paper, we propose novel partition and fusion method to enable fast MLP mixer inference on heterogeneous edge devices. Our case study on real-world setting shows the effectiveness and the efficiency of our method. Thank you. Thanks for listening. Is there any questions?
So in your slide, you mentioned 3 partition methods. And wondering what's the difference between this method and how do you select from this 2 methods?
Okay, thanks for your question. As you can see in this figure, different method has different memory and communication cost. You can see that we need to send data to devices, and when the computer is done, we also need to collect the result. So the input data and output data of fully connected computation will bring the communication cost. And then the width of the dense layer will cause the memory cost, mean memory cost. So you can see that data partition has the smallest communication cost, and the model partition has a higher communication cost but lower memory cost. And how we choose this model? Because we need to, because data partition method has the smallest communication cost. So if each devices have enough memory resource, we will choose data partition first. Thanks for your question. Is there any questions?
Okay, thank you so much. We have come to the end of the session. Thanks for all the wonderful presentation and big applause from everyone. I would like to thank all our volunteers as well to conduct this session so smoothly. And once again, thanks a lot for attending this session. I would like to remind you that we have a poster session later today. So you can meet the authors there and you can ask all your difficult questions over there. Thank you so much. Bye.